Very much for the kind introduction. Today I would like to show you a uniform fatigue damage tolerance law for additively manufactured and cast aluminium silicon materials. My presentation hereby is divided into 4 parts, starting with the motivation, then the experimental strategy, then the results, and at the end a summary and a conclusion of the results. Aluminium silicon alloy have a good strength and a low density, moreover a good corrosion resistance, and therefore they are promising candidates for lightweight constructions. Here you can reduce the weight approximately of around 40% compared to steel materials. Hereby, with additively manufacturing as well as casting, for example die or sand casting, you can reach this reduction in the weight by near net shape manufacturing. Moreover, with additive manufacturing you have the possibility of bionic structuring as you see it down here. However, for both processes the problem are process-induced defects. It means you need to know how the defects affect your lifetime, and the best would even be if you would have a uniform design law for additively manufactured and cast materials, and how you can enable this I would like to show you today. Hereby we use the approach of Murakami-Noguchi for estimation the fatigue limit of aluminum alloys, and moreover the approach of Shiozawa. Hereby you plot the stress intensity factor at the failure initiating defect over the number of cycles to failure divided by the defect size, and with this you can estimate the high cycle fatigue performance including the defect influence. Hereby the stress intensity factor at the defect is calculated based on the square root area approach or the Murakami approach with the following equation. We tested additive manufactured material, hereby laser-based powder bed fusion, PBF-LB, aluminium silicon 10 mg. Moreover, for die and sand casting we investigated aluminium silicon 10 mg and aluminium silicon 7 mg. Here we at the beginning characterized the microstructure, the defects, the hardness, as well as the quasi-static and cyclic stress strain curve to evaluate their influence on the fatigue performance and the fatigue damage tolerance. The fatigue tests were performed at a resonant fatigue testing system, mainly at a stress ratio of -1, but additionally to evaluate the mean stress effect we tested between -2 to 0.5, and with electrographic investigations we determined the failure initiating defect size of the specimen. Hereby at the beginning we start with the standard alloys for additive manufacturing and casting, that means aluminium silicon 10 mg and aluminium silicon 7. Look at the microstructure. Here we have the same scale for all materials, sand casting, die casting and additive manufacturing, and we see a huge refinement of the microstructure. Here around 0.5 microns to 100 microns for SC3. Here we have to look in detail to see the microstructure. The hardness was all in all comparable for all batches, and only the failure initiating defect sizes showed a big variation, and we show you how to include this within a reliable fatigue assessment of your material. Here we start with the quasi-static stress strain behavior. We see an increased yield strength for the casting material, while the ultimate tensile strength is significantly increased for the additive manufactured alloy. If we look at the fracture strain, that means the ductility, it is increased for the die casting material, and for the sand casting material it is comparable or even reduced to the AM material. Looking at the cyclic stress strain curve, there we could detect no significant change in the stress strain behavior for the AM material, just for the casting material, you see the plot over here, we could determine for all batches a significant cyclic hardening. That means that the cyclic yield strength is even more increased compared to the AM material, even shown by these two colors in the diagram. Just come to the fatigue behavior, SN curve or Walther curve, and here we see for the AM material the lowest fatigue performance. For the die casting material, although the defects are bigger, the fatigue limit and strength is increased. The same we could determine for the hip status. That means we further decrease the defects, and due to this the limit and lifetime is increasing. For sand casting, hip treatment, due to the defect sizes between DC and DC plus hip, we have an intermediate lifetime and fatigue limit. But when we compare this configuration with the AM material, comparable defect size, we directly see that the fatigue damage tolerance is reduced for the AM material. To be sure that it is really true and not due to a variation in hardness or something like that, we relativated the stress amplitude to the estimated fatigue limit of Murakami Noguchi. And by this, you see all the different casting batches laying now on one relative SN or Walther curve and show a significant increased fatigue damage tolerance to the AM material. Although we see that there are a lot of the fatigue limit cannot be estimated well with the Murakami Noguchi approach, and that there's an overestimation. And due to this, you have to be careful when you would like to use this equation. If you look at the Shiotsuba diagram, you see the same. Even here, the increased fatigue damage tolerance for the casting material. And our first explanation for this was the differences in the cyclic stress-strain behavior. And due to this, we used an elastic plastic fracture mechanical approach of Heitmann. Hereby we use the damage parameter together with the initial defect size to determine the J integral at the defect. And with this, and together with the approach of Schiebe, we then can include the mean stress effect as well the effect of the cyclic stress-strain behavior. To be capable of compare these results with the initial Shiotsuba diagram, we transform the J integral to a stress intensity factor, and the results you see in the following diagram. Now all the results lay more or less on one curve, and we have one uniform fatigue damage tolerance law to assess its behavior. In the next step, we would wanted to further validate this approach. Due to this, we even tested it for aluminium silicon 10 mg cast material SC10. You see over here, we could see that this material had an increased fatigue limit. But when we go to the Heitmann-Schiebe approach, here again, all the different alloys and process routes could be described by just one uniform fatigue damage tolerance curve based on this J integral based Shiotsuba diagram. In the next step, we then looked at the mean stress effect. Here, exemplarily shown for the additive manufactured alloy, and you see for the upper and lower limit from R-2 to 0.5 that there is a significant mean stress effect when we look at the Walther curve. This effect we can reduce by having a Shiotsuba diagram based on the Murakami approach, but still the mean stress effect is not considered. If we then go to Murakami-Schiebe, so Schiebe to include the mean stress effect, it is further improved. But first, with the Heitmann-Schiebe approach, when we further add the cyclic stress-strain behavior, a reliable fatigue damage tolerance design was possible. for some, now we are there. Okay, now we zoom in, you see again the results for the additively manufactured alloy, and moreover on the left side you see the coefficient of determination for the different approaches. And by taking the defect effect into account, you can improve the assessment, can further improve it with the mean stress effect based on the Schiepe approach, and with the connection of Heitmann and Schiepe, so the cyclic plasticity is included as well. Then we have the best assessment of the fatigue damage tolerance. With this, I would like to sum up the results. For the AM material, we have an ultra-fine microstructure. For our batch, the yield strength, the micro yield strength especially, was significantly reduced and lead to a reduced fatigue damage tolerance of these materials. Hereby, the Murakami-Noguchi approach could be validated for the casting material, however, lead to an overestimation of the fatigue limit for the AM materials. The Shiozawa diagram works too, but further validated that there is a decreased fatigue damage tolerance of the AM material. Due to this, we enhanced the Shiozawa approach by an elastic plastic fracture mechanical approach of Heitmann based on the J integral. And with this, we then could find a uniform fatigue damage tolerance lifetime law for AM and cast alloys, and could include the effects of defects, plasticity, and mean stresses. The next steps for us are to include further the effects of residual stresses, so and of surface roughness, so to keep this effect as well, and look if the model can work for this too. If you are interested in reading more of our research, here are some reference publications for you. Moreover, I would like to thank the DFG for funding this project, as well as my colleagues from Osnabrück, Aachen, Chemnitz, and Hamburg, the Fraunhofer, for the great support and the scientific discussions. And with this, I would like to end my presentation. Thank you for your attention and look forward for your questions.
Perfectly in time. We have time for 1-2 questions.
Please. Thank you for your clear presentation. We have also experiences with this type of materials, the same results, hardening, cyclic hardening, effect of mean stress. What is interesting, do you have experiences with loading in torsion? Because all these results are in tensile tensile test. In torsion, this aluminum material had very unusual behavior, that fatigue curve is over the tensile. Do you have some experience with this?
No, we don't have, but it's interesting to know, so that we will look in the future in this direction. Have you done multi-actual testing too? So
yes, also, and this effect also will be present in multi-axial.
Have you used your fracture mechanics approaches for?
No, they will be in testing.
Okay, all right.
If you apply the shear stress versus number of cycles of the fracture, you obtain the higher stresses like tensile stress.
Yes, thank you for the advice.
Very interesting. It depends probably of the orientation of the defects, probably.
Okay.
This,
for additive manufacturing, is there
this
an orientation defect?
Shear stress, this is multi-axial criterion.
Yes.
This problem.
This could be a good explanation.
Okay.
Thank you.
Any other questions from the audience? Okay, I have just one. When you showed, I don't know, the slide number, perhaps 12, go back.
No, just push, but
Okay. There was a comparison of all the plots SN until the approach.
The laptop just needs its time.
Okay. There was a change in the number of cycles to failure, starting from the Walther curve to the decay and other. Yes, this one.
Here's this.
Yeah. It's my fault. I don't understand why changing the coordinate axis, also the axis changing.
It was shown by Shiotzawa that when you have a crack propagation dominated material, when you integrate the Paris-Erdogan law, that at the end the result is that you should plot this stress intensity factor at the defect over the lifetime related to the defect size. And
so that was another axis.
yes,
Okay.
due to this, as it is a meter,
I missed
yes, then
change
it
of
increases.
the axis. Thank you.
Yes. And I further validated it for really crack propagation measurements, and when you don't relate it to the defect size, you have still some offset between the curves. And first with this relation to the defect size, all the curves lay over each other.
So there's a correction based on the defect size, both on the ordinate and also on the axis.
Yes, yes.
Okay. Thank you.
You're welcome. Thank you very much.
So thank you.